The ocean has a smell. You know it before you see the water. It reaches you first, something mineral, alive, faintly ancient. That smell has a name. It is called dimethyl sulfide. And it is made by life. Specifically, it is made by phytoplankton, microscopic marine organisms that produce dimethyl sulfide as they eat, reproduce, and die in the sunlit upper layers of Earth's oceans. The compound drifts upward into the atmosphere. It shapes cloud formation over open water. It has been present in Earth's air for hundreds of millions of years. Abiotic sources of dimethyl sulfide exist. But they are rare. Vanishingly small. When scientists find this molecule in significant concentrations, they find it where there is life. In March of 2025, the James Webb Space Telescope detected dimethyl sulfide in the atmosphere of a planet called K2-18b. K2-18b is not here. It orbits a red dwarf star in the constellation Leo. It is 124 light-years away. Light itself, traveling at 300,000 kilometers per second, takes 124 years to cross that distance. No human technology we possess or are building could reach it within any time scale that matters. And yet we can smell it. The team that made the detection, based at Cambridge University, published their findings with careful, precise language. They noted the signal. They listed alternative explanations. They called for further observation. They did not say what the signal might mean. That silence is the subject of this film. Not the data, the silence around the data. The gap between what the numbers suggest and what the scientists who produced them are willing to say aloud. Because in the history of this field, that gap has never been this narrow. And it has never been this loud. Science has been here before. Not here exactly, not with this molecule, not with this planet. But here in this posture. This hunched, careful, almost apologetic stance that researchers adopt when data arrives that is larger than they are prepared to receive. The history of the search for life beyond Earth is not a history of discovery. It is a history of almost. The year is 1996. A team of NASA scientists led by David McKay holds a press conference in Washington. They have spent months studying a meteorite, a chunk of rock blasted off the surface of Mars by an ancient impact, which wandered the solar system for 13 million years before falling in Antarctica. Inside it, they found structures. Microscopic, tubular, resembling, to their eyes, through their instruments, fossilized bacteria. The announcement lands like a detonation. President Clinton speaks about it from the White House lawn. The front pages of every major newspaper carry the image. The meteorite, designated ALH 84001, becomes the most studied rock in human history. Within 2 years, the consensus has reversed. The structures are almost certainly not biological. The organic compounds have almost certainly come from contamination. The scientific community, burned and embarrassed, retreats. It does not forget. 14 years later, a team of astronomers led by Jane Greaves at Cardiff University announces the detection of phosphine in the atmosphere of Venus. Phosphine, a gas that on Earth is produced by anaerobic bacteria, should not exist in Venus's oxidizing, sulfuric atmosphere unless something is making it. The paper clears peer review. The headlines begin again. This time the reversal takes weeks, not years. Other teams reanalyze the data. The signal is far weaker than reported, possibly a calibration error in the telescope. Greaves and her colleagues defend their work. The debate continues. But the damage is done. Another claim. Another retreat. Another entry in a ledger that the field carries silently, that it consults every time new data arrives and whispers the same warning. Be careful what you say. This is the atmosphere, not of Venus, not of K2-18b, but of the scientific community itself, into which the James Webb Space Telescope begins its work. The James Webb Space Telescope launched on Christmas Day, 2021. It is the largest, most complex space observatory ever built. Its primary mirror is 6.5 meters across, assembled from 18 gold-coated hexagonal segments. It orbits the Sun at a point called L2, 1.5 million kilometers from Earth, perpetually in shadow, cooled to temperatures near absolute zero so that its infrared detectors can register the faintest possible signals. It was designed, among other purposes, to look at the atmospheres of planets orbiting other stars. To take the light of a distant sun, filter out the starlight as the planet passes in front of it, and read what the planet's atmosphere has absorbed. A technique called transmission spectroscopy. A way of smelling a world from 124 light-years away. K2-18b was already on the list. It had been discovered in 2015 by the Kepler Space Telescope, a planet 8 times the mass of Earth, orbiting in the habitable zone of a red dwarf star. It was large enough that for years astronomers assumed it was a miniature Neptune. A rocky core buried under a crushing atmosphere of hydrogen and helium, with no surface, no ocean, nothing hospitable. A dead world, scientifically interesting, probably irrelevant to the question of life. Then Madhusudhan entered the picture. Madhusudhan is a professor of astrophysics at the University of Cambridge. He specializes in the atmospheres of exoplanets, the chemistry, the physics, the theoretical frameworks for understanding worlds he will never visit and cannot touch. In 2021, he published a paper proposing a new category of planet. The Hycean world. Hydrogen-rich atmosphere. Global ocean. Potentially habitable. Potentially teeming. The Hycean hypothesis was not universally embraced. Other researchers pointed out that hydrogen-rich atmospheres can be hostile, that the pressures and temperatures at the ocean surface might prohibit the kind of chemistry life requires. But it was coherent. It was testable. And it put K2-18b on the map as a primary target for the James Webb Space Telescope. Madhusudhan asked to observe it. The request was granted. The first observations occur in the summer of 2022. The James Webb Space Telescope stares at K2-18b as it transits its star, crossing the face of the red dwarf, allowing starlight to filter through its atmosphere and carry the fingerprints of its chemistry into the telescope's detectors. The data takes months to process. Madhusudhan's team works through it carefully, methodically, in the manner the field demands after Mackay, after Greaves, after every scar on the body of the discipline. In September 2023, they publish carbon dioxide, methane, both present in K2-18b's atmosphere, consistent with the Hycean model. A living, ocean-covered world could produce exactly this mix. The paper notes the findings with measured enthusiasm. It is the kind of language scientists use when they are genuinely excited and genuinely terrified of being wrong in public. And then, almost in passing, they mention something else. A tentative signal. A spectral feature at a specific wavelength that corresponds to a specific molecule. The feature is weak. The team acknowledges it may not be real. But it is there, and the molecule it corresponds to is dimethyl sulfide. The paper is careful to note that this detection is preliminary. It calls for further observation. It says the signal could reflect an unknown abiotic process. It does not linger on the alternative. The alternative is that something is alive on K2-18b. Here is what Madhusudhan did not fully advertise in the paper. His own models, the atmospheric frameworks he had built to characterize Hycean worlds, had not predicted a detectable dimethyl sulfide signal. They had predicted that even a substantial marine biosphere on K2-18b would produce dimethyl sulfide concentrations too dilute for the James Webb Space Telescope to resolve. The planet, by his own calculations, should have been hiding this. It was not hiding it. The signal was not just present. It was larger than his model said a living ocean should produce. It was larger, in fact, than his models said almost anything should produce. He had designed a framework to find life. The framework had told him life would be invisible. And then something showed up anyway, waving. He published anyway. Carefully. Quietly. With every caveat the field requires. The community responds with precisely the caution decades of false positives have trained it to deploy. Other researchers note that dimethyl sulfide can form through abiotic chemistry, through reactions between sulfur compounds and hydrogen in certain atmospheric conditions. The concentrations required are implausible, but not impossible. The signal itself may be noise. The spectral feature overlaps with other molecules. The error bars are wide. Sarah Seeger, an astrophysicist at MIT who has spent her career developing the science of biosignatures, puts the skeptic case plainly. A single molecule is not enough. Biosignatures must be understood in context, in the full chemical ensemble of an atmosphere, not as an isolated reading. One molecule can lie. Patterns of molecules, in concert, are harder to fake. She is right. And Madhusudhan knows she is right. And the signal is still there. In the winter of 2024, the James Webb Space Telescope observes K2-18b again. More transits. More data. More months of processing and verification, and the particular anxiety of waiting to find out whether the universe has played a trick on you or told you the truth. In March 2025, the second results are published. The dimethyl sulfide signal is stronger. Not dramatically stronger. Not beyond debate. But stronger, in the same molecule, in the same atmosphere, on the same planet, measured by the same instrument using a different data set. The signal has not gone away. It has grown. The paper is careful again. It is always careful. It lists alternative explanations. It calls for further study. It does not use the word the reader is waiting for. But something has shifted. Inside the community, in private correspondence and conference hallways, and the particular register of academic language that scientists use when they are struggling to contain what they actually think, something has shifted. One researcher, speaking not for attribution, describes the situation with a phrase that does not appear in any paper. He says, "The prior probability that this is nothing has dropped considerably. That is as close as anyone will come to saying it out loud. Here is what we know. The James Webb Space Telescope has detected a spectral feature in the atmosphere of K2-18b consistent with dimethyl sulfide. This detection has been replicated in a second independent observation. The signal is weak but persistent. The leading abiotic explanation, photochemical reactions involving sulfur, requires atmospheric conditions that K2-18b does not obviously possess. No confirmed abiotic source has been identified that adequately accounts for the concentration the data suggests. Here is what we do not know. We do not know that the signal is real. Spectroscopy at this level of sensitivity operates near the edge of what the instrument can resolve. The error bars permit an interpretation in which the feature is noise. We do not know that K2-18b is a Hycean world. The category remains theoretical, contested, and unconfirmed by any direct observation. We do not know that dimethyl sulfide cannot form abiotically in conditions we have not yet imagined. And we know something else, something harder. We will never resolve this the way we would want to. There is no sample return from K2-18b. No rover, no lander, no instrument that could touch the water, if there is water, and return with the evidence that would end the argument. The distance is not merely inconvenient. It is absolute. Even at the speed of light, a message sent to K2-18b today would arrive in the year 2149. A response would return in 2273. Every answer we will ever have about this planet will come from light. Photons. The faint shadows that molecules cast in a star's spectrum as they pass between us. The next generation of observatories may help. The extremely large telescope, now under construction in Chile's Atacama Desert, will have a primary mirror 39 meters across. It will be able to study K2-18b's atmosphere in greater detail than the James Webb Space Telescope, to look for the ensemble of molecules that Seeger describes, the chemical concert that would be difficult to explain without biology. The Nancy Grace Roman Space Telescope will add new capacity for atmospheric characterization. Each instrument will narrow the uncertainty. But narrowing is not closing. There is a threshold, unwritten, unagreed, but understood by everyone in this field, at which the evidence becomes sufficient to say the word. Not to prove it, not to be certain, but to say. The most parsimonious explanation for what we are observing is that this atmosphere was made, in part, by living things. The word is life. No one has said it yet about K2-18b. Not in a paper. Not in an official statement. The gap between the data and the word remains, narrow, charged, and absolutely silent. Step back now. Widen the frame. Consider what has been described. A molecule. A spectral line in a graph produced by a telescope 1.5 million kilometers from Earth. A number, a wavelength, a concentration, a signal-to-noise ratio, that corresponds, in the chemistry of our own planet, to the breadth of the sea. If this is what it might be, then the discovery of life beyond Earth will not have announced itself with drama. It will have arrived in a data file. It will have sat in a spreadsheet for months while a team of careful, frightened scientists checked and rechecked the arithmetic. It will have been published in a paper written in passive voice, hedged with caveats, accompanied by a list of alternative explanations that everyone involved privately considered unlikely. And somewhere in that paper, between the methodology and the conclusion, will be a sentence that future generations will read the way we read the sentences from 1543, when Copernicus suggested the Earth was not the center of the universe. A sentence that seems, on its surface, almost deliberately understated. A sentence that contains, compressed within its careful language, the full weight of what it costs to know something the world is not yet ready to hear. We have been looking for life in the universe for as long as we have understood what life is. We have built instruments and aimed them at the sky. We have sifted through signals and studied rocks and calculated the odds and revised the odds and argued about what the odds even mean. 124 light-years away, on a world we cannot visit, in an ocean we cannot see, something may be living. Eating and dying and releasing, as life does, the molecules that mark its presence. Those molecules rise into the atmosphere. The atmosphere catches the light of a red star. The light carries the signal across the dark. It falls into a mirror. We read it. The question that remains is not really about K2-18b. It is about us. About what we do with a signal that is too important to ignore and too fragile to confirm. About the kind of civilization we are, whether we are the kind that waits for certainty before it believes, or the kind that has learned, finally, that certainty is not what the universe offers. It offers evidence. Partial, flickering, incomplete. And somewhere out there, if we are reading it correctly, something is alive.